We can.
Can, sir.
Okay. So my account is now subscribed, so I'm able to record. So I've started recording, and I'll share the link after we're done. So today we're dealing with something very easy, and we're dealing with what are called Euler equations. So what is an Euler equation? Is an Euler equation. So it's an equation of the form.
So I've written equation.
So I meant Euler, yeah. So it's an equation of the form. So I sent out the notes. Sorry for sending them late. Next time I'll do better. So it's of this form. So ax squared. So a is just any real constant plus bxy plus cy. So this is y prime is equal to 0. So it's of this form. So a is just any real constant, and it need not be 0 because we want this to be a second order. If this is 0, then you have a first order. But another equation is a second order of this form. B again is a real constant. C is also a real constant. So a x squared is the coefficient of y double prime. Bx the coefficient of y prime, and c is the coefficient of y. So what we usually do under that power series thing, when we want to check, can we solve this using the power series? What we do, we want to make the coefficient of y double prime 1. So we divide through by x squared, and this division is proper since a is not equal to 0. So we divide through x squared, a x squared. So 0 over x squared is just 0. So what do we get? We get y double prime plus, so this is going to be b over ax. So there's an x squared, so remain with x. Then y prime plus c over a x squared, y is equal to 0. So this is what we remain with. So now we analyze this coefficient. So you have b over ax and c over ax squared. So these coefficients now, are these analytic? So question is, are they analytic? And the answer is no. So by analytic, what do we mean? Can you write this? Can you write these as power series? So the answer is no. And to give maybe a simple reason, it could be that if you write this, so a over b, so this is over x, you can write this as a over, or b over a x to the power -1, c over a squared, you can write this as c over a x to the power -2. So it's these coefficients. Remember, for the power series, we said we don't want negative exponents. So this is a problem. So the first thing we established, these are not analytic, and because of this, we cannot use power series method. We cannot use the power series method to solve Euler equations. So are we together this far? Is this clear?
Yes. Yes, sir.
Okay. So if we cannot use power series method, how then can we solve such equations? So this guy Euler did some research, which is a whole lot of work to
Sir,
read. Yes,
Excuse me, sir.
yes.
On the conclusion, repeat again. I didn't understand.
So what exactly? Your question needs to be more specific.
Okay, like are they analytic? So on the way you were taking the b over ax is equal to b over a x to the power -1. What
Yes.
was your conclusion there?
They are not analytic. So these two are not analytic. They are not analytic. And this analytic word should not scare you. What it just means is, can I write these as a power series? Power series so that which has 0 or positive exponents. And the answer is no, you cannot. So they are not analytic, and because they're not analytic, we can't solve them using power series method. Because for the power series method, we require that these analytic, you write them in power series, then plug them into your equation. Have I answered your question?
Yes.
Okay, great. So I was saying this guy Euler did some research, and there's a lot of work written on this, but the conclusion he made was that how do we solve this? We solve this in the following way. What we do is we first begin by assuming, so we assume that x is equal to 0, and that our solution is of the form, and solution is of the form, so it's not in form of the power series, but it's in form of an exponent. So solution is of the form y of x is equal to x to the r. So once you get this, if this is the solution, then you know that y prime here is going to be, so it's the usual, drop the r, so x r minus 1, then the y double prime is r minus 1, x to the r minus 2. Then if you plug these back into your equation, so maybe I should use this. No. So if you plug these into your equation, so what was your equation? So your equation is a x squared y double prime plus b x y prime plus cy is equal to 0. So in place of y double prime, I put what I got here. So it will be a x squared, then this will be r minus 1, x to the r minus 2, plus bx, what is y prime, r, x to the r minus 1, then plus c, y is x to the r is equal to 0. We can remove the brackets, so multiplying this out, what do we get? So we have a r minus 1. So here you've got two exponents, so you've got x to the 2 and x to the r minus 2. Same base, so you can add the exponents, and it's going to give you x to the r. We do the same for this one, so the coefficient is br. So multiplying x by x to the r minus 1, we get x to the r. And this is x, this is c, x to the r is equal to 0. The x to the r is common in all these three terms, so we can factorize. And we have ar minus 1 plus br plus c is equal to, O. Then the x to the r, x to the r is equal to 0. So, so it was important that when beginning we made the assumption that x is equal to 0, because this is where we use it now. So how do we use it? If x is greater than 0 and this expression here is equal to 0, it means that this can be 0. It means that this has to be 0. So this happens. So I'll say if and only if this is equal to 0. What we have in the brackets, AR r minus 1 plus PR plus C is equal to 0. So what you get here now, if you examine this, what you get is a quadratic. So this is a quadratic equation in R. So the variable here is R in R. And so if you had to solve this, you expect 3 possible things, as you know from your knowledge of quadratic equations. 3 possible solutions. So the first one is that once you solve this, your solutions are real. Both your solutions are real and distinct. Then you can get double root. So you only get one solution. So we call it double root of the quadratic equation. And the third possibility is what? What do you think is the third possibility when you're solving a quadratic equation?
Complex roots.
Complex roots. Thank you very much. Complex roots. So you've got 2 different complex roots. The good part is they are conjugate of each other. So let's deal with each of these cases. We start with the real and distinct. What happens if you have real and distinct roots? So Euler says in his findings, so real and distinct roots.
Sir, sorry, you can just put the previous page on camera so that we can be able to see.
Okay. This one, right?
Yes.
So all these are in the notes. You're done?
Yes.
Okay. So I was saying real and distinct roots. What happens? So is that equation, you solve it, and it means, so what was the equation? It's A r minus 1 plus PR plus C is equal to 0. So you solve it, you get 2 solutions, real solutions, say R1 and R2. Then Euler says that your solution, or he says the fundamental set of solutions. Fundamental set of solutions will be of this form. So it's like you get 2 solutions. So your y will be, y of x will be C1. So you just add the constant because the constant doesn't change anything. And x to the first root plus C2. Again, you can add the constant and x to the second root R2. So when you get
sorry, sir, I don't understand that part.
Which part?
When you have the real and distinct roots.
So remember, what we are trying to solve is this equation. So what we're trying to solve is this Euler equation. And according to the research done by Euler, he says your solution should be of this form: x to the y, x to the r. So if you plug this in back into your into this equation, you get this quadratic equation. You solve this, and we're assuming that you get two real distinct roots, R1 and R2. So Euler says in that case, you've got two solutions and you can sum them up to get this fundamental solution. So let me write this properly. So you get y of x is equal to, so you can add this constant, because by adding this constant, you're just making it more general. Instead of having the constant 1, then this is x to the R1 plus C2 x R2. Is this okay?
Yes, sir. Thank you.
Now,
Yeah.
sir, where did these two in the notes came from?
Which two?
In the notes, there is 2, a plus 2 after the equation.
Where? On which page? So meaning we have to go back to the notes.
Page 4 of 13.
Page 4 of 13.
Yes.
I don't see it. How come I don't see what you're seeing? Me, I'm still on page 1 of the notes. So which two are you talking about? So help me to understand what you're saying. Which two are you talking about?
The same equation, I will screenshot it and send it.
Okay, please do. Just do that now on WhatsApp, we see.
All right.
Does anyone else who has seen the two?
Sir,
Yes.
hello.
Yes.
The notes that you sent me, I saw they ended up to 4 pages.
Yes.
Now that one which has got 13, I don't know where it is coming from, because I went through the notes, they went up to 4 pages. So the 13th one, I don't know, maybe it's using a different document.
Oh, maybe he's using last year's notes.
Maybe.
Anyway, you should verify, but this is in essence the theory. So let's do an example on this and see that we don't lose track. So suppose you're given, and this example again is in the notes. So you're told to solve. So this is an IVP, standing for initial value problem. So you're given initial conditions. So it's like this: 2x y double prime plus 3x y prime minus 15y is equal to 0. And your initial conditions are that y of 1 is equal to 0 and y prime of 1 is equal to 1. So what these initial conditions help you do, it's like you're solving a specific solution. So in this case, once you're given these initial conditions, then you have to find what your constants are. In this case, you have to find what your C1 and C2 is. In the case of power series, usually our constants were A0 and A1. So with these initial conditions, you can find what your A1, what your A0 and A1 is. So, so once you see this, something like this, you don't use, so the key thing here, solution. So you have to identify, say this is an Euler equation. Euler equation. And the point here is that we cannot use power series method. So you have to be very careful. So power series method has got, you have to know on which equations this method applies. So Euler equations is one of them where it doesn't apply. So you cannot use power series method.
So, sir,
Instead,
how can we tell that it's an Euler equation? Like, what's the most evident thing that's an Euler equation?
it's of this form. It has to be of this form. It's ax squared y double prime plus 3x y prime. Oh, I'm sorry. So it's ax squared y double prime plus bx y prime then plus cy is equal to 0.
Also,
So in
it's
this
always
case,
an x squared.
yes, it has got this squared and this x. These constants can be anything.
Okay.
The only possibility we exclude is a being 0. So in this case, we see that your a, in our example, that is our a is 2, our b is 3, and our c is negative 15 for this Euler equation. So it's easy to see. It's like identifying when you have a quadratic equation. Actually, this takes the form of a quadratic equation, only that you've got this y prime, y double prime, y prime, and y. Okay, so back to the equation. So this is the equation. So how do you go about solving this solution? You have to assume that instead of you having a power series, the solution is of this form as an exponent of this form. And in this case, then it means that y prime is r x to the r minus 1, y double prime is r minus 1, x to the r minus 2. So if this is the case, you plug this back into your solution. What do you get? You have 2 x squared, then this is r minus 1, x to the r minus 2, plus 3 x x to the r minus 1, then plus or minus 15 x to the r is equal to 0. You do away with the brackets, what do you get? You get 2 r minus 1, then this is x to the r, then plus, so this will be 3r, then x to the r minus 15 x to the r is equal to 0. Factorizing, you have 2r minus 1 plus 3r minus 15 x to the r is equal to 0. So this is the quadratic you get, and you have to solve this quadratic to find what your solutions to this quadratic are. So in this case, this implies that 2r minus 1 plus 3r minus 15 is equal to 0. Let me expand this. Expanding, I get 2r squared minus 2r plus 3r minus 15 is equal to 0. So this is 2r squared plus r minus 15 is equal to 0. How do I solve quadratics? I have to factorize it. So how can I factorize this quadratic equation? So if you remember in your high school, what were we doing? We say a product. So it's a minus c, a times c, you get minus 30. And your sum is 1. So what are your factors? 6 and negative 5, right? So this becomes 2r squared plus 6r minus 5r minus 15 is equal to 0. And so I factorize the first part, I get 2r, I remain with r plus 3, then minus 5r plus 3 is equal to 0, so that I get 2r minus 5, r plus 3 is equal to 0. Are we together? Am I too fast?
Yeah, you are quite a bit fast.
I've got another meeting at 15. So anyway, let's not rush. But this is not, we're just solving the quadratic here. So solving the quadratic, we factorize, we get this. And once we have that, then we can equate the individual factors to 0. So this means that 2r minus 5 is equal to 0, or r plus 3 is equal to 0. So solving this, you get r is equal to 5 over 2, or r is equal to negative 3.
Excuse me.
Yes?
Isn't the minus 5 in the bracket there supposed to be positive, following that the r on top is positive?
No.
No, it's negative.
Replacing the factor.
It's negative, yeah. Because we picked it up from here, right? So this is fine.
Yeah.
Our factors are 6 and negative 5, so I can write it like this. Then when I factorize this part, there's a factor of 2r, then here there's negative 5. Yeah, so it's negative.
Okay, thank you.
So we found our two solutions of the quadratic equation. What does it mean? So remember, we said our solution in this case will be of the form y is equal to c1 x to the r1 plus c2 x to the r2. So you can consider this to be r1 and r2, so that your solution for this specific problem you've been given, your general solution that is, so this is the general solution and not the specific solution, is equal to, so C1 constant, x to the 5 over 2 plus C2 another constant, then x to the negative 3. So we've done the important part. We found the solution as Euler says, but we've been given these initial conditions. So what are the initial conditions? The initial conditions are y1 is equal to 0 and y prime of 1 is equal to 1. So if y1 is equal to 0, so y1 there, I have y1 here, meaning where there's x, I put 1, I still get back the ones, so it will be still 1, so it will be c1, plus where there's x again, I put 1, still 1, so I get c2. So c1 plus c2 is equal to 0. Y prime of 1 is equal to 1, so I need to find the derivative here. So y prime of x is, I bring down the exponent, so it will be 5 over 2 c1. Then what remains here, I'm subtracting this minus 1, so I get x to the what? 3 over 2, right? 3 over 2 plus, I bring down this, so I get, so it becomes negative, so minus 3, then c2 x to the minus 4, because it's minus 3 minus 1. So this is the first derivative. Then first derivative, you plug in 1, so you have y prime of 1. So what are we doing again? Where there is 1, where there is x, we plug in 1. So this will be 5 over 2 C 1. 1 to the power 3 over 2 is 1 minus 3 C2 1 to the power negative 4 is 1. And this should equal to 1.
So,
yes. Yes.
Yes. How are we using the y of 1 is equals to 0 and the y of 1 is equals to 1?
So yeah, this is what we're doing. So the first one is y of 1 is equal to 0. The second one is y prime of 1, not y of 1. It's y prime of 1 is equal to 1. So this is my y. I found my y, my general form of y. So if y1 is equal to 0, meaning where there is x here, I put 1, it means that c1 plus c2 is going to be equal to 0. Because if you plug in 1 here, you have 1 to the 5 over 2, which is 1, 1 to the negative 3, which is 1. So you get c1 plus c2 is equal to 0. For this one, you have to find the first derivative. So we found the first derivative by the usual dropping the exponents, then subtracting by 1. So this is what we got. Once we get the first derivative, we plug in 1 in the first derivative, and this is what we got. So we end up with two equations, which are, so the two equations are, there's C1 plus C2 is equal to 0, and then we have 5 over 2 C1 minus 3 C2 is equal to 1. Is that a question?
Yes, it's a question. There on the general formula.
Yes.
Can you go back on the general formula?
The general solution.
Yes, the general solution on top. That formula on top, how do you get from y is equal to c1x to the power r1 plus c2 rx, the power r2 to yx is equal to c1? Then
this is just x. This is not rx to the power r2. This is just x.
Oh, okay. Thank you. That's where I was confused.
Sorry, I didn't write it properly.
No,
So this was, I was saying this gives you, so these equations give you these two equations, and if you look at them closely, then should be able to see that these are simultaneous equations, so you can solve them simultaneously. So how can we solve this? We can say, we can say C2 from this equation, from the first equation, C2 is equal to negative C1. Then we plug this into this equation. So it's going to be 5, so let me write 5 C1 over 2 minus, so C2 is negative C1. So this becomes plus 3 C1 is equal to 1. Then common denominator is 2, so you have 5 C1, then 2 there, 6, so plus 6 C1 is equal to 1. And we get 5 C1 plus 6 C1 is 11. C1 is equal to 2. So our C1 is actually 2 over 11. So we found our C1. C2 is the negative of C1. This means that C2 is negative 2 over 11. So once we have this now, we have to go back to the general solution, which was this one. In place of C1, we have 2 over 11. In place of C2, negative 2 over 11. So our specific solution to this initial value problem is 2/11 x to the power 5/2, then minus 2/11 x to the power -3. This is the specific solution. And we can check that this is going to work.
But please move up a bit. We can't see the solution down.
Oh, okay, sorry.
Yeah,
sorry.
son.
Yes.
Yeah. Going back to the quadratic equation that we solved.
Mm-hmm.
How do the R1, the one to make us R1 and the one to make us R2?
It doesn't matter. You can interchange them. Anyway, anyone is fine. You still get the same. You still get back the same thing.
Okay.
Yes. So you find it's a quadratic. You find two solutions. Whichever selection you make to be R1 or R2 doesn't matter.
So can you explain again from on this page, on the part where you said it's a simultaneous equation, from where 5/2 C1 minus 3 C2 is equal to 1. After that, I don't understand what happened.
Okay, so this is our simultaneous equation, and what happened to this thing? Okay, this is our simultaneous equation. And as you know, there are several methods you can solve this simultaneous equation. I chose to use, what's the name of this method? I can't remember. But anyway, what I did is I used the first
substitution method.
Substitution, eh? Yes. Yeah. So what I did is I make C2 the subject here using the first equation. Once I make C2 the subject, I replace what I found to be C2 in the second equation. So when you do that, this is C2 here, it becomes negative C1. So in place of this C2, you put negative C1, you get this. Once you've done this, now you have your C1, you can solve this because the same variable or the same constant. So we just went ahead, we did the addition, we solved it, we found C1 is 11/2. After we found our C1, we go back to this equation, which says C2 is equal to negative of C1. So if C2 is 2/11 and C2 is the negative of C1, then C2 must be negative 2/11. So that's how we conclude that C2 is negative 2/11, and we just replace them in the equation.
All right, thank you.
Now, sir, one thing that I want to ask is, do they specify to say use power series method or use Euler's equation? Because some of us, we can jumble things.
You don't have to jumble, you have to know where, or you have to, so the point is you have to identify your Euler equation. That's the key point. You have to be able to identify. It's not so difficult. Like I said, it's not like a quadratic in some way. When you see a quadratic equation, it's so easy for you to identify. In the same way, it should be easy for you to identify an Euler equation. And if it's an Euler equation, then we know we can't use power series method. We have to use this theory by Euler. So it's not complicated. So to answer your question now, do they specify? Usually, yes. Like the first question is use power series method. And maybe somebody will ask to say, solve this Euler equation. Once somebody says Euler equation, they've already told you it's an Euler equation. When you see it, you can also be able to tell that it's an Euler equation, then you use this theory. Have I answered your question?
Yes, sir, thank you.
Okay.
Sir.
Yes.
like on Euler equation, I'm going to be given the y1, those conditions, y1 is equal to 0 and y prime of 1 is equal to 0. Like always,
not
or maybe
always. Not always. Not always. So these initial conditions can be given.
If you're not given, you have to.
So if you're not given, then what will be your solution? Your solution will just end here. Will just end at the general solution. It will just end here. Meaning you won't go ahead to find what your constant C1 and C2 is. So these initial conditions are not specific for, it's just a pity you didn't do ordinary differential equations in second year. So what I want to say is that these initial conditions are not specific to Euler equations. You can even be given these initial conditions for an equation which requires power series method. It's possible. I wish I had put some in the tutorial sheet. So it's possible, and you find the constants. In that case, you usually see that your constants are A0 and A1, so you'll be finding what your value of A1, A0, and A1 are. Have I answered?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Do you have any other questions? So we've done real distinct roots. So real and distinct roots. We're remaining with a case where your quadratic equation gives you double root or gives you one root, so double root or one root, and also the case where you get complex roots. So we'll do these in the next class. I'm sorry I have to end here because I'm attending another online meeting at 15. So we'll do these in the next class. The notes are there. You can still read about them. Then you can ask me during class. And after we're done this, we can give you another assignment and see how we move on. So I'll post the link to the video on WhatsApp and on Moodle. I also need the first two links. Are they 2 or 3? I also need the first two links so I can post them on Moodle. Is this okay?
Yeah,
Yes,
it's
sir.
fine. So there are 3 links.
Yes, 3 links. Yeah, there was one where we had 2 links. So the people were recording them, or any of you have them, if you can just send me a WhatsApp, then so what I'll do is I'll upload them to my drive, then send the link in case the other drives misbehave. Okay, so next class. So I'll end the meeting.
Send the link.